Hooray, we did in the end. So we're going to look at strong and weak acids today. So we've got the pH scale behind us. Quick recap that acids are lower than 7 and alkalis are above 7, or bases. So again, remember the difference between a base and an alkali is that an alkali is just a soluble base. So it's something that will react with an acid that dissolves in water. All right. And again, these colours here are what colour the acid and alkali goes when you add universal indicator. So many students forget that key point, all right? They'll say, what's the difference between acid and alkali? Acids are red, alkalis are blue, all right? Well, there's an acid, it's colourless, all right? Here's an alkali, or technically a base, it's a white powder, all right? So it only goes these colours if you add universal indicator to it. So we're going to be looking at strong and weak acids today, all right? Because a lot of people use the word strong and weak to mean concentrated, and hopefully we're going to remove that type of misconception today. So I'm going to do 2 different experiments today with a strong and a weak acid. So here's my strong acid, that is hydrochloric acid. And here is my weak acid. This is called acetic acid or ethanoic acid. Okay, so the first thing I'm going to do is, going back to our pH scale, remember that the further away from neutral we are, so the closer to 1, the stronger the acid. So some acids will have a really dark red colour when I add universal indicators. Some will have like an orangey yellow colour. All right, so let's look at the difference then. So here I've got my strong acid. I'm just going to add a few drops of universal indicator. So 2, 3. So I have 3 drops of that. And you can see it's gone a lovely pink colour. So it's probably down towards 2 or 1, all right, around that type of area for pH. Do the same thing to the weak acid, and to make sure that my results are valid, I'll add the same volume of universal indicator. Okay. And it's very difficult to see, all right, but you should, hopefully, if I just hold it up a little bit, yeah, that's much better, with the light behind. This one is a slightly paler colour. It's a bit more orangey in colour, okay? So it is a weaker acid, despite the fact their concentrations are the same. So I've got the same volume of acid with the same amount of acid particles dissolved in it. So, but you can clearly see one is a much darker pink than the other, okay? So again, this one has a pH of around 1 or 2. This one will be 2 or 3. So again, the next thing I'm going to do is I'm going to now have a look at their reactions or reactivities with sodium carbonate. So another bit of, let's do another extra bit of chemistry while we're at it. So recap, if an acid reacts with a carbonate, you get a gas produced, and that gas, well, the key is in the phrase carbonate, will be carbon dioxide. And how can I test that gas to see that it is carbon dioxide? That's a question for you all to think about, all right? I haven't got an answer. So I'm going to get some fizzing or effervescence in a moment. How can I then test that gas, if you watch the previous videos, to see whether or not it is carbon dioxide? I'll give you a massive clue. Lime water. Yeah, I'll bubble the gas through lime water. So I'm just going to get a tube of lime water here. Oh, that's far too much. Put a bit of water away. Beautiful. Lovely colourless solution. And then I'm going to roughly, and I should have used scales for this, I'm going to add the same amount of, same mass, because I know that I've told you off using the word amount in chemistry. So if it's liquids, we talk about volume. If it is solids, we talk about mass. So I'm going to add the same mass to each. So again, you're looking for how quickly it reacts with the carbonate. So how quickly do we get bubbles? Yeah. So you can see that's reacted quite quickly, and that's with the strong acid. Yeah. Okay, I'm now going to add the same mass to the weak acid. And you can see it is much, much slower, which is hopefully something that you can understand. All right, or something to appreciate, that weaker acids aren't as acidic, so they react a bit slower. So you can see not much bubbles at all there. Obviously, if I was to add an excess of the carbonate, and now you can clearly see, hopefully, the difference in the colours. So this one, strong acid, very, very pink. This one, much more orange in terms of its colour. Okay. Obviously, if I was to add an excess of this carbonate, it should go from being an acid to neutral to maybe even being basic at the end. So if I add a big spoon of that, okay, and another big spoon to that. Okay. Oh, forgot to collect some of the gas. Put that in there. And then quickly cover. Whoop, give my lime water a shake. Yeah, perfect. Love chemistry, it just works, doesn't it? So the gas that I've just tested has made lime water go cloudy, so it was carbon dioxide. And then you can see, if I just give, that's gone slightly neutral, but there's some unreacted powder at the bottom, so I'm going to give that a quick. Now you'll notice there's no more fizzing anymore, so all the acid has reacted. And what I'm left with now, if we go back to the pH scale, is probably around there, 13, 14, maybe 11 to 12, something like that. And this one is still reacting. So it's a slower reaction because it's not as strong. But you can see that it goes yellow, green, blue, and eventually we're there. Yep, so I've neutralized the acid, I've added an excess of base, and we've ended up with a high pH solution. So what is going on with this? We're going to have to talk about strong versus weak acids. So to do that, I'm going to sort of show you, all right, an equation to show that, to illustrate this point. So I've got two different chemical equations here. One is for a strong acid, and one is for a weak acid, right? Well, first things first, let's start by looking for commonality. What do they have in common? What makes them an acid? Okay, well, what do they have in common? Both of these things, so this is hydrochloric acid, all right? So that's hydrochloric acid. And this is ethanoic acid. Yeah. What do those two acids have in common? Use these equations to help you. All right. What do they both do? So whether it's hydrochloric acid, which is HCl, or ethanoic acid, which is CH3COOH. Because it links into what our definition of an acid actually is. And hopefully you can all see they both release H pluses. Yeah? And that's the definition of an acid. An acid is a H plus donor. It's an H plus donor. It's something that donates H pluses. All right? And a H plus is just a proton. Yeah, so what they're actually, they just lose hydrogen ion, not hydrogen atoms, hydrogen ions. So effectively, HCl is going to break apart into H plus and Cl minus. This thing, CH3COOH, is going to break into H plus and CH3 minus. So they both donate H pluses. Brilliant. But why do we call this a strong acid and this a weak acid? Because these equations help illustrate the definition of strong versus weak. So we know they're both acids because they're H plus donors, but one is strong and one is weak. And why is that? What is the fundamental difference, the key difference between these two chemical equations? Right? Hopefully you guys can spot it. It's all to do with that symbol there. Right? That symbol has a very important place in chemistry, right? We call that symbol lets you know that the reaction is reversible. So we had a whole topic on reversible reactions, okay, but it's a good time to practice. So it's half an arrow pointing to the right, and then underneath it, half an arrow pointing to the left. That's the symbol for a reversible reaction. Yeah, so it is a reversible reaction. And that's quite important because this reaction up here is not reversible, right? Which means that it can't turn back. So if I was to have 100 of these HCl's, every single one of them will break apart into its ions. So if I've got 100 of these, I'll end up with 100 of those. If I've got 100 of these things, these weak acid molecules, will I ever end up with 100 of these? Well, no, because as soon as that's formed, can't they just recombine and go back to the start? Yes, they can. So there's a big difference then to how they ionize, how they break apart. So a strong acid fully ionizes, which means it fully breaks apart. If I had 1 million of those, exactly 1 million of them would break apart. If I had 1 million of these, it wouldn't be 1 million, it wouldn't be anywhere near that. It'd probably be closer to 1,000, right? So the dissociation, or how they ionize, how they break apart, is different. So for a strong acid, they fully ionize, they fully split apart. So what could our definition for a weak acid be? If a strong acid fully ionizes, what could we use, or what words could we use to describe a weak acid? Okay. So what word we use? If a strong acid fully breaks apart, then a weak acid, so it's definitely going to ionize. But then what word would we use to describe the level of ionization? Not fully ionizes? That could work. Is there a word that we can use to describe that? I think we should use the word partially, because that's the word we use at A level. So I think you guys should be entitled to that now. So partially ionizes. So will I ever end up with 100% of these things over here? Well, no, because as soon as they're formed, because the reaction is reversible, they can recombine and end up back here. Okay. So again, if I had 100 of these, I'll end up with 100 of these. If I have 100 of these, I'll probably only end up with 2 or 3 of those. So that's the difference, okay? So the amount of concentration of H plus in a solution, I'm going to recap what that word means in a moment, tells you about the pH, all right? Because go back to our pH chart. For a strong acid, what do you expect the pH to be? So the pH for a strong acid is around 1. It will go really dark red with universal indicator. The pH for a weak acid is around 3. Yeah? So pH is just a measure of how much H plus there is. So hopefully you understand now why strong acids have a lower pH. Because the more H plus you've got, the more acidic it is, so the lower the pH, the further away from neutral you will be. Similarly here, we've still got some H plus, but we haven't got as much as the top one because some of this would have recombined, would have gone backwards. So again, it will still be an acidic, it'll still be an acid, but it'll be weakly acidic. Okay? So let's have a look then at concentration. So strong and weak is all to do fully ionizes, partially ionizes. Let's look in a bit of detail at solutions then. So, quick recap from your possibly year 7 days, maybe year 8, about what a solution is. So it's solute plus solvent makes solution. Yeah, so let's go with an obvious one. Sugar plus water makes sugar water. Yeah, solution. It's all the solid has dissolved, it's mixed together. All right. Now, I'm hoping you guys get this idea that different solutions could have different masses of solute dissolved in it. So we could have well, let's go for a cup of tea. We've got 2 identical cups of tea. One has got 1 spoon of sugar dissolved in it, and one has got 2 spoons of sugar dissolved in it. Which one has the most sugar dissolved in it? Well, it's the one with 2 spoons. So we would say that that is more concentrated. So concentration is just a measure of how much of that we have dissolved in water. That's all concentration is. Yeah. So if I had a beaker of water and I put in 10 grams of salt and dissolved it, and then I've got another beaker of water, I put in a kilogram of salt and dissolve it, that one is more concentrated. There are more salt particles dissolved in that volume of water. Okay. So concentration is how much of the solid acid is dissolved in the water. So forgive this very crude diagram. You've got two beakers here, and you notice that the volume of water in both is the same. But this one has a little bit of acid dissolved in it. This one has lots of acid dissolved in it, so it is more concentrated. You probably use the words concentrated and dilute to talk about squash. It's the same thing, yeah? A tiny bit of squash, you end up with quite a pale solution. A load of squash dissolved in it, same volume of water, you'll notice, you'll have a much more concentrated. So there's the difference between, and I know that some people will refer to squash as strength. Oh, that's a bit strong. No, 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 don't say that. Say it's more concentrated. If you've got, you know, half water, half squash, yeah, you say, oh, that's very concentrated. Don't use the word strong, because strong means something else when we're talking about acids. Yeah, strong means that it fully ionizes. So we could, in theory, to summarize this, hopefully you can see this, dilute just means a low concentration, i.e. not much dissolved in water. Concentrated means that there's quite a lot. You see the difference between these two beakers? Yeah? Imagine they're dissolved in water. That one, there's only about 8 particles in it. This one, there's nearly twice as many. It's much more concentrated. Yeah? So that's the difference between dilute and concentrated. And here, we've got weak and strong. So a weak acid is one that partially ionizes. So which means that, if you have a look here, you've got green attached to white. Have all the green and whites detached? Have they fully ionized? Well, I hope I can see there's a white just there, and that's about it. The rest are all stuck together. But over here, look, for a strong acid, it has fully ionized. So all of the green and whites have separated. They are fully broken apart. So just having a look, if I circle all these H's, or H pluses, whoa, ignore that. Okay. I knew that would happen. I knew this would happen. Yeah, there we go. So you just clearly see, this beaker has got one H plus swimming around. That beaker has got a lot more H pluses swimming around. So that is a stronger acid. So this pH, stop drawing on the board, Mr. Scrimshire. That pH would be a lot lower, for reasons we'll come on to in a moment. Right? But the one thing you do notice is there's the same concentration of both. I.e., if you count the number of green circles, so there's 1, 2, 3, 4, 5, 6, 7, there's 8 molecules in there in total, and only one of them is broken apart. In here, there were 1, 2, 3, 4, 5, 6, 7, 8. There were 8 molecules, and all of them had broken apart. So again, when you're dealing about acids, you need to know whether it's weak or strong, dilute or concentrated, to work out the pH. Okay, so these are both, that's a strong acid, that's a weak acid, all right, and they have the same concentration. Okie dokie. So what is the relationship then between concentration of H plus and pH? Well, there's a table here, all right, and I'm going to expand on it in a minute. So if the concentration of H plus is 0.10, and the units are moles per decimeter cubed. Now, you've not come across the concept of a mole before. A mole, all right, it's not a small furry animal. What it is, but in chemistry, it's just a number. A mole is just how much of the solid is dissolved in a litre of water. A decimeter cubed is a litre. So you can clearly see here, as we go down, there's less and less. These numbers are getting smaller and smaller, which means there's less solute, dissolved in the water. Okay? But then as that number goes smaller, okay, what do you notice about pH? The pH value is getting bigger. All right? And hopefully you can see why it's an inverse scale. So the more H plus you've got, let's go back to the start. Let's go right back to the start. The more H plus we've got, the stronger the acid. So the further down here it will be. And then as we get less H plus, the pH goes up and up and up and up and up. I can prove that with a graph as well. So if we have a look here, all right, there we go. So again, I've written all these numbers in. So you see we've got 0.1 moles per decimeter cubed, so that's 0.1 moles dissolved in a litre of water. And as it gets more and more dilute, please note these numbers are getting smaller. It's 0.1, 0.01, 0.001, all the way down to 0.13 zeros and then 1. As the amount of H plus goes down, the pH goes up. Because that's all pH is. pH just stands for like parts hydrogen, all right? And it is an inverse scale. So the more hydrogen you've got, the lower the pH. So the more hydrogen ions you've got, sorry, the lower the pH. So if you look at this graph here, you can clearly see as I get more and more dilute, what I'll do is I'm going to discard all that. Like that. As you get more and more dilute going this way, the pH is going up. Okay? So the pH is going up. So in an alkali, would you expect there to be much H plus? Well, no, very, very little. Okay? And this just proves it. Okay? So it's a nice little graph there to prove the relationship between concentration of H plus and pH. Okay? You could write it in standard form as well. So again, the relationship there, I've written them out as full decimals. I know in maths you do standard form quite a lot. So, for example, this one, let's choose one. Let's choose that one. To write it in standard form is basically just saying how many decimal places there are. So if we focus on that one there, so it's 1 times 10 to the minus, and then how many places have I moved the 1? So we'll do a 1 there. So I've moved it 1, 2, 3, 4, 5, 6. Yeah. And this one here, look, that will be 1 times 10 to the minus, and then I'm going to put a 1 there. How many positions have I moved it? 1, 2. Now, pop quiz. Do you notice a pattern there between pH value and concentration? Is there a pattern? Yeah. It's probably easier in standard form. So I now can see a pattern, so I know I can just put here 1 times 10 to the minus 2. 1 times 10 to the minus 9. Yeah. Can you see that in standard form, the number of places you've moved it to is the pH? Yeah. So effectively, the number of zeros before you get to 1 is the pH. So if I just take any one here, let's take this one, for example, 8. So I'm expecting there to be 8 zeros, all right, in my concentration. 1, 2, 3, 4, 5, 6, 7, 8. Oh, wrong, can't do one. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 zeros there. So again, it tells you there's a scale here. As you dilute your acid by a factor of 10, so that could be if I have 1 mil of acid and then 9 mils of water on top of it. So as I dilute it by a factor of 10, dilute acid by factor of 10. So hopefully you can see that all I'm doing each time is divide by 10. Divide by 10. Divide by 10. Yeah? I'm hoping you can see that because that's exactly the formula that I put into Excel when I did this table. Right? As you dilute by a factor of 10, the pH goes up by 1, plus 1, plus 1, plus 1, plus 1. Yep. So there's a really, 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 really niche relationship there. As you dilute by a factor of 10, so as you divide the concentration by 10, the pH goes up by a value of 1 each time. Okay? Right. Beautiful. So, just to finish then, okay, I've got a few questions, and then we're going to have a look at the answers. So, what is the difference between acid strength and concentration? So again, think about the answer. Write the answer if you want, all right, and I'll go through them in a couple of minutes. What happens to the volume of gas produced if the same concentration and volume of acid is used with a weak and strong acid? So again, think back to this, all right? I had exactly the same volume, I had exactly the same concentration. What would happen to the amount of gas produced? What happens to the rate of reaction produced? So this links to the speed of the reaction. So when those two reacted, was there a difference in terms of how quickly they produced? And then why is the pH of hydrochloric acid lower than that of ethanoic acid of the same concentration? So why was, at the start of the lesson, that pink and that one orange? Okay. Whilst you're doing that, I will look at any questions that you've put. Do we get work over the summer holidays? Not really. There'll be some things for you to be getting on with, but there won't be like massive amounts. And well done, Simran, for spotting, all right? Number of zeros equals pH. Yeah. So, acid strength versus concentration. So the strength of an acid is a measure of the degree of its ionization. Strong acids fully ionized, weak acids partially ionized. Concentration is the measure of the number of moles of acid in a litre of solution, or how much, or the mass of the solid acid is dissolved in a litre of water. Those two reactions that I demonstrated earlier, so question 2, would have produced the same volume of gas. Because I had the same amount of acid particles in both, I roughly had the same amount of solid added, so it will have produced the same volume of gas. But linking to question 3, the stronger acid, because it had more H pluses swimming around, reacted much faster. So weak acids, it did fully react, so it did change purple in the end, but it was a lot slower. Okay, right then. So that's just a quick run through, all right, through, well, fairly detailed run through actually, through strong and weak acids, okay? I will hang around for the next few minutes, see if anyone's got any questions, all right, because your task for this week is to do that, which is to summarize that topic, which we've done today, in 5 sentences, reduce it to 5 words, and then reduce it to 1 word. So hopefully I'm just asking you to watch this lesson and then write 5 sentences, 5 words, and then 1 word. Are there any questions about this?